I came across this question online. It is a proof by induction question. Part A wants us to show that the square root of n plus 1 minus the square root of n is greater than 1 over 2 square root of n plus 1. Okay, now we can show that this is true, okay, if and only if, and we can play around with this inequation, multiplying square root of n plus 1 on both sides. Okay, so we do that. Square root of n plus 1 times the square root of n plus 1 minus the square root of n, and that is going to be greater than 1 over 2. Okay? So I'm essentially doing a bunch of biconditionals until the very last statement I get is true. Okay? Because all of these are equivalent to each other. So if the final statement is true, if the final inequation is true, then this inequation is true. Okay? So that is what I'm going to do right here. I'll distribute, and I'll get n plus 1 minus the square root of n plus 1 times the square root of n. Okay, if and only if. I can subtract 1/2 on both sides, so I get n plus 1/2. And then I will move this part to the other side. So this is going to be greater than square root of n plus 1 square root of n. Okay, so essentially I subtract 1/2 on both sides. Okay, and then I added root n plus 1 root n on both sides, so this is what I have right over here. Okay, now what I'm going to do is that I'm going to square both sides, if and only if. So if I square this side, I'll get n squared plus 2 times 1/2 times n, which is just n, plus 1/2 squared, which is 1/4. And this is greater than, if I square this side, then I'll get n plus 1 multiplied by n. Okay, and this is just equal to n squared plus n. And what's nice is that the n squares cancel out on both sides, the n cancels out on both sides, and what I get is I get 1/4 is greater than 0. And that's true, 1/4 is greater than 0. So we end up with a true statement at the end, okay? And because with all these biconditionals, each statement is equivalent to each other, because this statement is true, then the first initial statement is also true. Okay, so part A is done. And now part B says we want to use induction, proving using induction, using the result from part A, that 1 plus 1/2 plus 1/3 plus ... plus 1 over n is less than the square root of n for every n greater than or equal to 7. Okay, now I'm going to rewrite 1 plus ... plus 1 over n using sigma notation. So I'll say we are trying to show that the sum from k equals to 1 to n of 1 over k, all right, is less than the square root of n for every n greater than or equal to 7. Of course, here n is a natural number as well. Okay, so we have the base case, which is when n is equal to 7. All right, so then we have the sum from k equals to 1 to n of 1 over k, where n here is 7, which is the same thing as 1 plus 1/2 plus 1/3 plus 1/4 plus 1/5 plus 1/6 plus 1/7. Okay, now what you could do is, if you don't have a calculator, you can for sure have a common denominator and write it as a fraction, and then do some multiplication to find out its decimal expansion, which I already did, which is approximately 2.59. Okay, and then the square root of 7 is approximately equal to 2.65. Okay, now if you didn't have a calculator, what you could have done was, okay, let's say if you sum up this part over here, you get something like a over b, all right? And then you want to compare if this is larger or greater than the square root of 7, okay? Then you just have to square both sides, okay? Just square both sides, all right? Square root of 7 squared is 7, all right? So you just have to compare these two numbers, and you'll figure out that 7 is going to be greater than this sum squared, which means that the sum if I square root both sides, is going to be less than the square root of 7. Okay, this is also a biconditional statement. Okay, all right, so we conclude here that the sum, all right, is going to be less than the square root of 7, so the base case holds. Now, what we want to do is we want to do the induction step. Okay, so for the induction step, we do need the induction hypothesis. So we want to suppose that this sum from k equals to 1 to n of 1 over k is less than the square root of n for some n greater than or equal to 7. Okay, so once we have this, what do we have? Okay, then let's suppose what this is. Okay, so k equals to 1, the sum, k equals to 1 to n, 1 over k, n plus 1, actually, because the induction step is talking about the n plus 1th term, all right? Should probably put capital letters here. Okay, then we have this, okay, is going to be equal to the sum from k equals to 1 to n of 1 over k plus 1 over n plus 1, okay? I'm essentially just substituting this k with the n plus 1, because this is the final term, okay? So I replace k with n plus 1. So this is going to be summing from k equals to 1 to n of 1 over k, and then this is plus 1 over n plus 1. So this is a perfect time for me to use the induction hypothesis right over here. This right here is the induction hypothesis. Because if we assume that for this particular n, some n greater than or equal to 7, that the sum, okay, is less than the square root of n, then right over here, I have this sum right over here. So it's going to be less than the square root of n plus 1 over n plus 1, okay? So essentially, this right here, the sum being less than the square root of n is my induction hypothesis, and I'm simply adding 1 over n plus 1 to both sides of this inequation, okay, of this inequality. Now I do want to point something out over here before I keep going forward, because I'm going to make a claim and say that 1 over n plus 1 is going to be less than 1 over 2 times the square root of n plus 1. Okay, so I'm saying that this is smaller than this over here. Of course, I have to add the square root of n on both sides. Okay, so I haven't shown that yet, but this is a very important step to make. So let me show that right now. So let me just point this out. I'll call it a lemma. All right. So 1 over n plus 1, I make a claim that this is going to be less than 1 over 2 square root of n plus 1. This is true if and only if I could reciprocate both sides and I get n plus 1 is going to be less than, or greater than, because you flip the inequality when you reciprocate, 2 square root n plus 1. And then I can square both sides. Okay, n plus 1 whole thing squared is n squared plus 2n plus 1 greater than squaring this part. I get 2 squared, which is 4, times, and then n plus 1, which is equal to 4n plus 4. Okay, moving everything to the left-hand side, I get n squared minus 2n minus 3, which is equal to, well, if I factor this, I get n minus 3 times n plus 1, and that is going to be greater than 0. Okay, so we see right here that the roots to this are minus 1 and positive 3. Okay, now because n is a natural number, I don't really care about this minus 1 part, but I do care about what happens when n is greater than or equal to 7. But if we plug in some values, we see that anything greater than 3 if I plug it into here, it's going to be positive. Okay, it's going to be positive for anything greater than 3, because I'm curious as to what happens when n is greater than or equal to 7. Okay, 7 is over here. Okay, so it is going to be greater than 0. So any number, any positive integer, any natural number greater than or equal to 7, when you plug it in here, it's going to be greater than 0. Okay, so this is always going to be true. So because this statement is always going to be true, because n is greater than or equal to 7, then following the series of these biconditionals, okay, if and only ifs, then we get that this is true. Okay, whenever n is greater than or equal to 7, this statement holds, which means this statement holds too, because I'm simply adding root n on both sides of this inequality. Okay, so this is beautiful. Why is that? Because I can actually use part A over here. Okay, because I have square root of n plus 1 over 2 square root of n plus 1. Now, over here, because part A is true, right, I can simply move this negative square root of n over to this side, and that becomes a, so if I just essentially move it over, right, this is plus square root of n, okay? Okay, so this is good. So what we have here is that this is going to be less than the square root of n plus 1, okay? Now, this is very good because it's essentially following the same format as what we had over here, right? So instead of n, right, I have n plus 1 over here, okay? Which means that the n plus 1 term is also going to satisfy this inequality over here, okay? Which is good, because I simply shown that, okay, if this was true for a specific n greater than or equal to 7, then is it the case that the next term will also follow this inequality using the induction hypothesis, which is something we assume to be true, right? Is it true? Yes, it is. So is the n plus 1th statement going to be true? And yes, it is, okay? I'm not simply just going to plug it in, right? Because that would mean I will do it blindly. But here, I am using a series of facts that I already know to be true already. And I got to this conclusion over here, which is what I want. Okay, so therefore, by the principle of mathematical induction, okay, what was my thing? Okay, my statement, the sum from k equals to 1 to n of 1 over k is always going to be smaller than the square root of n for every n natural number n greater than or equal to 7. Okay, and that is it. What a fascinating question to prove.